Today we're discussing regular polygons and some formulas that we're going to use to apply to them. Before we do that though, we need a little bit of review and to know what a regular polygon is. So our review, the formulas that we looked at yesterday dealing with angle measurements are going to be really important for us today. If we wanted to figure out the sum of the interior angles, so all the angles added up that were inside the polygon, we use the formula n minus 2 times 180. Number of sides, take away 2, multiply that by 180. If we want to know the exterior angle sum, it's always 360. Those will be important because now today we're going to look at what a regular polygon is and how we can use these formulas to give ourselves a better idea. First, we need to know what a regular polygon is. A regular polygon is a polygon that is both equilateral and equiangular. Now, equilateral means that all of the sides are the same. Equiangular means all the angles are the same. So if we know that we have a shape that is both equilateral and equiangular, then that polygon is regular. If only one of those conditions are met, it's not regular, but it could still be equilateral or equiangular. It just can't be both if both conditions are not met. Most of the time when we have a regular shape, we're just going to call it regular whatever it is. So regular octagon, a regular nonagon, whatever. There's two exceptions to that. The two exceptions are when we have a quadrilateral, we call that a square, because a square is both a rectangle and a rhombus. It's equilateral and equiangular at the same time. And for triangle, we call it an equilateral triangle. Now notice that for triangle, it's equilateral, but it's also equiangular at the same time. And that is the only time that that's going to happen, that we have a shape that's guaranteed to be equiangular if it's equilateral as well. Okay, and again, any other polygon that is not a quadrilateral triangle, we call it regular, whatever it happens to be. All right, before we get into the formulas, I want to show you a demonstration and how these formulas work. Let's start with the exterior angle. So we've got our exterior angle listed out here. So here's our pentagon, five-sided shape. And you'll notice that each of our exterior angles are the same. Now total, they're going to add up to 360 because that always works out for any kind of polygon. The exterior angles add up to 360. If I wanted to find out what each one was, it seems like I might be able to rearrange this formula to find out what it is. So let's see if this works. Let me go to the next shape. And you notice my numbers change a little bit, but the 360 is still the same. So the exterior is always 360, and it seems like if we take the number of sides and divide that over here, that'll tell us what each exterior angle is. So our exterior angle formula appears to be 360 divided by how many there are, which makes sense. If all the exterior angles are the same and they all add up to 360, then we take 360 divided by how many there are, and that tells us what each one measures. Now you'll notice as we increase the number of sides, the exterior angles are getting smaller because they still have to add up to that 360. So if you have more angles, then each one has got to contribute less to it. So as we increase more and more sides, our exterior angles are getting smaller. Now compare that to an interior angle. Now for an interior angle, the sum is not set. It's going to keep changing. So we know that an exterior angle together has to add up to 360. Can't get any bigger than that. But interior angles, it's variable. It depends on exactly what shape we've got. There is a relationship, though, between the interior angles and the exterior angles. So let's go back to that hexagon. We knew that the exterior angle was 60, and the interior angle is 120. Now for the heptagon, we knew that we had a 51-degree exterior angle, and notice our interior angle is 129. For an octagon, we had an exterior angle of 45, the interior is 135. Seems to me like the relationship between the interior and the exterior angle is that they're going to be supplementary. So if I take an interior plus an exterior, I get 360. I'm sorry, 180. Interior plus exterior is going to be 180. So from this, you'll notice as we add more sides, the interior angle increases. And that makes sense because the exterior angle is getting smaller. They have to add up to 180. So if I keep taking a smaller number away from 180, I get a bigger number. So one way to figure out what the exterior angle or interior angle is we can take the interior angle, subtracted from 180, and that's going to get, I'm sorry, the exterior angle subtracted from 180, and that gives us the interior angle. Our other option is, you'll notice the similar logic that we had before. We're going to take our sum, and we're going to divide it by how many sides we have. So we're going to take this n minus 2 times 180 and divide it by n. So here is that listed out. So our two formulas that you need to know from this section, E, that represents one exterior angle, is going to be equal to 360 divided by n. N is the number of sides. For interior, you have two ways to figure this out. One way is you take your exterior angle and subtract it from 180. So 180 minus 360 divided by n. Your other option, if you can figure out the sum of the interior angles, the n minus 2 times 180, you can divide by how many there are. And that will tell you what each one measures. And that's where these formulas come from. Again, it's not just made up. It's the sum divided by how many there are. So the 360 divided by n gives you the exterior. The n minus 2 times 180, the sum of the interior, divided by how many there are, gives you one interior angle. Because they're regular, we know all the angles are going to be the same.